Now that you know Lisp, we can have a look at the Shelley networking protocol specification. This document is attached into the video notes, and we can also compare it to my Lisp implementation of this protocol, which is a simplified way of dealing with the node. You will notice by the table of contents, it is quite an extensive document, but it will give you a very clear idea on how to communicate with the node. I will briefly introduce some important aspects for our minimal way of connecting to the node. As you can see from this picture, well, the way two nodes communicate, or any client to the node would communicate, is by sending some kind of message to the node. So it's really basic to understand what happens on the wire. How do you send these packets of information? And there is a specific format, the wire format, as shown in this simple diagram. We start on the first 32 bits of this message, given the transmission time, and it's just a clock time with a resolution in microseconds. The next thing we have is 1 bit is a flag, that is the mode, and it's to distinguish are you the initiator where you have a 0, or you are the one responding where you use a 1. Follows is the mini protocol ID. That's how you identify what specifically are you communicating for. A payload length, and of course the payload itself. And it means you have to chunk your messages in, of course, 2 to the 16 minus 1 bytes. That's all. That's very simple to implement. And the missing thing, the mini protocol ID, we have in this table where I am going to implement the node to client protocol. And we only have handshake, chain sync, local transaction submission, and local state queries. Let's see how this compares to the implementation code. I know it's Lisp, and Lisp is a very dense language, but it's also something that you can fit on your head. My entire reference implementation fits in around 370, 350 lines of code, discounting the header comments. So it's really small. It's not production code. It doesn't do a lot of error handling or type checking or any other particular thing that you would need for production code. But it's something small enough that works, that you can fit your head around, and it's a great place to get started. This should be very familiar. I'm just here in def bar, I'm defining a variable, and the association list where I match the symbol, handshake, chain sync, and so on. These are my protocols and the number they represent. You see they match. I have, this is particular to Cardano, the hard fork era's names. Ouroboros network, this is a struct. This struct is where I will contain the network connection, and for relevant purposes, I will hold, of course, the process that does the network connection. This is an Emacs internal thing. It's how we do socket communication on Emacs. And some additional data like the network magic that I need to communicate with Cardano, the protocol version, type of connection, whether I am a client to node or a node to client, and the particular era. This is how I define functions. So define starts defining a function, how I'm going to name it, arguments, and documentation. I'm going to do just a connection to a remote entity, depending whether remote, the input I give it the vector I am connecting to a node over TCP IP, and I am another node. If I give a string, it's probably I'm connecting to the local socket of the Cardano node. That's where my example in this guide will be focused on. Then I, of course, create my container I described before, here the Ouroboros network. I write the network magic, copy the type I received from the resolution, and I make a connection. This is just very internal Emacs. I make a network process that handles the connection. Wherever I'm connecting, I specify the remote. That's where I'm calling. Coding. Filtering is what happens when I receive a message from the system. This is very simple. I open a temporary buffer. I made it a single byte because Emacs is a text editing program, so it has support for Unicode and multi-byte strings. But because all the communication here is binary, I have to enforce that what I receive as a string, as a message, has to be unibyte. And then I'm collecting the reply, which expects this shape, and the Sentinel just watches what happens to the connection. Let's jump to the collect reply. This is this small function. You see I'm defining the function collect reply. And now it has to imitate what I have on the wire format. Let allows me to define variables. This is the timestamp. And it says, well, consume out of the CBOR 4 bytes and transform that into an int. That's how I get the transmission time. I know the transmission time is 32 bits. That's 4 bytes. Mini protocol ID, it's 2 bytes. The size of the payload is again 2 bytes. I decompose what protocol am I working. I extract that out of the ID. First, by logical XORing it with a big number to remove the mode flag. I ask on the Ouroboros protocols, well, what was it? And I take the symbol of the protocol. Finally, I capture the payload. I take the substring from the point where I am after moving 8 bytes and what I expect or I receive and size length from the message. And that's pretty much it. I create a new buffer, and what I'm going to do there is just copy into that buffer the payload and move forward into the temporary buffer. And that's it. That's how I collect reply. And the way I send, of course, a message to the server is the inverse function. I do get from my connection the network process. I convert my data, that was an argument, from the eLisp object to a CBOR. This is a beautiful thing about Lisp, that I can have functions with all these characters, have an arrow. The protocol is, again, I look the protocol in my Ouroboros protocols to get transformed into a number. And the time is, I get the time of the system, make it seconds. This is a threading macro. It means it will just take the one input into the next function, into the next function, into the next function, instead of having it nested like its usual Lisp way. This is just more readable, and I only need to read left to right. So then I send to the process the string, and here's again, I'm respecting the wire format. 4 bytes for the time, 2 bytes for the protocol, 2 bytes for the payload, and the payload itself. That's it. That is the way we communicate. Let's look further on the specification on the right. What are the protocols? Protocols are defined as state machines. And a state machine is really a glorified flow control. Instead of imperatively defining with if and else's how things are going to progress into your system, you make a state machine. And the state machine has the beauty of transforming your flow control into a data structure. And that is what you see on this illustration. For example, the ping pong protocol. It says, well, when I start my state machine on my client, I start in the idle state. By the message ping, I act and send the server something. I enter in the busy state where the server has agency. That means I wait until I receive a reply, the message pong from the server, where I am back to my idle state. And I can loop around this state, or at some point through the message done, I just stop the state machine. This is a flowchart. This is how the execution moves. But as I said, in a state machine, you transform this into a data structure. And a data structure is much more easy to parse, version control, reason about, edit, than it would be editing a lot of conditional statements. Now, I am not going to implement the state machine runtime in my example because I don't need it for the simplicity of the example. But I do have to respect the messaging. And that is what you see in my reference implementation. Instead of having the state machine, I just sequentially do the steps. The very first protocol we need to implement is the handshake. When you open a connection, you have to go over the handshake with the server. It's a very simple state machine. You start it, you go enter your proposing state. By the message of proposed versions, you enter in the confirm state where you're waiting for the server to tell you something. But the proposed version message is something you also send to the server. And the server will reply you with the accepted version or the refused version. This reply version seems to be nowadays obsolete. Depending on that, well, you're done. Hopefully you have accepted handshake, otherwise refused, you have to restart everything. Okay, and that's it. This translates into this table. As I say, the flow control becomes a data structure. And let's look at the messaging. Messages are specified in the CDDL encoding. This is the concise data description language. That's the way we describe CBOR. CBOR is how we represent our objects for the communication on the wire within the Cardano network. And I'm interested in the handshake for the node to client. I have handshakes propose, accept, and refuse. Those are my three messages. And propose, accept, and refuse. Okay, handshake mini protocols. This is how I define the handshake. I say, well, send the payload, the protocol handshake, and the function propose versions. A proposed version, as you see on the specification on the right, is an array, a vector of 0 and a version table. And that is the shape I'm going to follow here. 0. And then what is the version table? The version table, as specified down here, is a map where every key is a version number and every value is the node to client version data. Version numbers currently supported in Cardano node 1.35 are from 9 to 13. Those values get flagged on the 15-bit. So the version number are these big numbers, 32,777. And that's what I do. For example, if I have a node to client connection, I will do an A list where I have the version 10 exclusive org on the 15-bit so that I can flag it on. And if you see this backtick, that's equivalent to the quote. This is called quasi-quote. When I quote an expression, it just gives the form back. When I have a quasi-quote, which is the backtick, every time I have a comma, it means it evaluates the expression following. Thus, I have here the version numbers. I want to evaluate 10 logical XOR. That's the 32,778. I have two protocol versions, the 10 and the 13. That's depending different nodes. I'm in mainnet or on the testnet right now at the time of recording. Testnet is already in node 135 and hard forked to the Vasil or the Babbage era. And then the magic is the network magic. This is a parameter we have to set when connecting to the node. And that is the proposed version message. And that is something I send when I'm doing the handshake. Now, as you know, from this flow representation, well, I send the payload. I accept the outputs. That means this is a waiting part, a waiting command that will wait until I receive something. And I will have a look at the reply, see what is going on. So the reply function handler is here. What does the reply look like? Well, I could have accepted version. That is an array of 1, the version number, and node to client version data. Node to client version data is the network magic itself. And that's it. pcase is a pattern matcher. So I take the reply, the parsed reply. I say, okay, again, quasi-quote. If I have an array where the 1 is there, and I will put under version, that's why the comma is here, whatever value is there, and then magic. And I just take out the version. This means the accepting version. Rever is this local function I defined here. When I am in node to client, it says, well, if I'm version 1, return the 1. Anything else, do again a logical XOR to the number I have. That's to go from the big number back to the 9, 10, 11, 12, 13. Or a refuse, right? And refuse is an array, you see here on the right, of 2 and refuse reason. I do the same in my code, 2 and the reason. This is a threading macro. Because what kind of reasons could I have? Let's look at the reasons on the specification. 3 types of reasons: version mismatch, handshake decode error, refuse. And that's again the same thing. It's a vector of 0 and the version numbers that the server would allow, or a 1 and the version number and a string telling me what is wrong. So I have this formatted version. Or the 2 is again a version number and a string where I get the connection refused. And once I have chosen for these things, well, I can return a user error. There's a handshake failure.